So we have looked at capacitors, we've looked at resistors, we've looked at inductors. Now we're just going to see what happens if instead of powering them with a constant voltage, we power them with an alternating voltage. So in a circuit, that is a battery or an ideal battery, and it will give a constant voltage. This is the symbol for an alternating current voltage source. So instead of always providing, a voltage kick where one side is 1.5 volts higher than the other side or 9 volts higher than the other side, the voltage across an alternating current source changes not only magnitude and direction, and usually it's going to have a form like this, where the voltage across it at any given point in time is going to be equal to V aught, or V sub 0, its voltage amplitude times the cosine of its angular frequency times time. So for the mean household power for the United States, the frequency would be 60 hertz. But the angular frequency, remember, is not the same as the frequency. So it would be 120 pi inverse seconds. So hertz is how many times something happens per second, and it is a unit given for frequencies. So it's very similar to inverse seconds, but it's just for frequencies. And the voltage, there's not just one way of describing it. There are at least two pretty common ways of describing voltage in AC sources. So this is, in this equation, is the voltage amplitude. So if we've got voltage time something like this, that would be the amplitude. The height of the wave from the middle to its maximum value. More commonly stated than the amplitude for a lot of uses, is the root mean square voltage. So if you were powering something with this, say powering a resistor, sometimes that resistor would get the full amplitude. Sometimes it would get a low voltage across it or no voltage at all. So because power across the resistor is equal to the voltage squared divided by the resistance. If you want to know the average power usage, the average voltage doesn't give you what you need. It's the average square of the voltage. So that's what VRMS is, root mean square, or the square root of the average of the square of the voltage. It works out to be root 2, a factor of root 2 less than the peak. So when someone describes the voltage that a house receives as 120 volts, they're actually talking about the root mean square voltage, which is more useful for determining the average power of something than the amplitude. So there's just two different ways of describing it. It's easy to convert one to the other. It's just a factor of the square root of 2. So if we have this power source and we make a circuit with a resistor out of it, and our current is also going to be the cosine wave, because the current through a resistor is directly proportional to the voltage across it from V equals IR. So the current through the resistor and if we just start with this as our assumption, there's going to be our current through the resistor is changing as a cosine wave, and we can look to V equals IR. So the voltage across it is going to be the current amplitude times the resistance times cosine of omega t. And this is just the voltage amplitude. So for our resistor, the current follows along the same pattern as the voltage. So current and voltage in this graph would need to be represented by two different units. So which one's taller or shorter is entirely meaningless because they have different units. But the important thing to see is when one of them hits 0, the other one hits 0. When one of them's positive, the other one's positive. They go along with each other in phase. And for power, is equal to current times voltage. So power is going to be equal to our current times our voltage. And we've got cosine times cosine, so this gives cosine squared. And if we wanted to get the average value of the power, for average power, we would need the current amplitude, voltage amplitude times the average value of cosine squared. And the average value of cosine squared is 1/2. Uh, if we break up this 1/2 into root 2, 1 over root 2 times 1 over root 2, we can see that it is the RMS current times the RMS voltage, which shows, again, why the root mean square value is often used, because it's makes finding average power quite easy. Any questions so far on alternating current? Different ways of stating our voltages and currents? Let's work with it a little bit. So simple circuit, we've just got our AC source and a resistor. So what would the peak current that you would get and the average current through this circuit? Work it out. So our voltage is our voltage amplitude times the cosine of our angular frequency times time. And the voltage amplitude is √2 times the RMS voltage. So √2 times 120 volts is very close to 170 volts. Voltage right like that. So this function, it's going to have a average value of 0. Cosine is positive just as much as it's negative. And a peak voltage of 170 volts. We just want to get our current on its own. So 17 amps times the cosine of its angular frequency times time. And this is going to give a peak of 17 amps and an average of 0. Any questions on this one? Last equation, last page. I think it was average power is equal to IRMS. And this holds if you've got an AC circuit with just a resistor. Things will get more complicated. And let's make them more complicated. So resistors, not our only circuit element. We've worked with inductors, we've worked with capacitors. So with resistors, the voltage across it is proportional to the current through it. So if voltage goes up, current goes up exactly the same, keeping pace, directly proportional, Ohm's law, it's all nice. Inductors work differently. The voltage across it is proportional to the change in current through a resistor. So when the voltage is highest through an inductor, that doesn't mean that the current is highest. That means current is ramping up the fastest. So you're going to get a current peak after a voltage peak. So for an inductor, the current lags the voltage. In a capacitor, the voltage across a capacitor is not directly proportional to the current flowing into it. is proportional to the amount of charge it's stored, or how much current has flowed into it, the integral of current. So the voltage across it reacts to what the current has been. So for a capacitor, the current is leading the voltage. So the peak in voltage happens after the peak in current. So once all the current has flowed into it, that's when you get the greatest voltage. Also, resistors were not frequency dependent at all. Capacitors, if you try and have current flow into a capacitor just indefinitely, the voltage across it gets higher and higher, and it gets harder and harder too. Whereas inductors, they resist changes. So it's very, very difficult to make a rapid change in the current across an inductor. So to get back to our inductor, AC source, and just an inductor. So making Kirchhoff loop for the circuit, our voltage across our AC source plus the voltage across our inductor sums to 0. So an approach that I use is treating the voltage as a given and trying to get to a current that way. For AC circuits, it's often easier to start with the current and use that to get to your voltage. So if we just have our current be our current amplitude, and just have this given, and we could later figure out what these quantities might be, but this is our current, and our phase is going to be set by the current. Then voltage be our inductance, and we need the derivative of this, so cosine is going to give us minus sine. So omega sine. We're just cleaning that up. Where the voltage and the current don't have the same peaks. Our voltage amplitude is dependent on the current amplitude, also dependent on the angular frequencies. So for a given current, you need more voltage to work at a higher frequency. it's harder and harder to make rapid changes. The more rapid the change, the more difficult it is through an inductor. And graphing them, if we have our current, our voltage. Doesn't match up with it. So you can see whatever the voltage does, the current does the same thing a quarter phase later. So the voltage starts at 0, a quarter phase later, the current is at 0. So this is the current lagging the voltage by 90 degrees or by a quarter phase.
You said that it was the current is a quarter phase behind, or the
Yeah,
voltage is?
the
Okay.
current is a quarter phase behind for an inductor
Okay.
because
Thank
the
you.
derivative of it responds to the voltage. So it takes the current time to catch up to it.
Okay, I get that.
And if you just look at these graphs, the red peak is, behind the black peak in time. All right. Little conceptual check-in I have for how inductors and capacitors would work at different frequency. Rotation angles. So it's not in a geometric sense. It just uses the same mathematical function. So the language of sines and cosines is just very good at dealing with this. We're not dealing with literal triangles in physical space. We're going to get to phasors pretty soon, which is a really cool way of putting these offsets in phase, which one comes first, which one comes second, in a more geometric picture. But literal rotation, literal angles, no. It just follows a sine function or a cosine function. Yeah. If you set up one of these in a cosine pattern, everything else will follow in a sine or a cosine pattern. The second graph I drew is for an inductor. And it has the voltage peak having at a different time as the current peak. Whereas for the resistor, the first graph I drew of VNI, the voltage peak happened at the same time as the current peak.
How long would the period be in terms of W?
So omega, which is a lot like a W, so it's forgivable to call it W, is 2 pi times the frequency. And our frequency is 1 over the period. So our angular frequency is 2 pi times 1 over the period. So our period is equal to 2 pi divided by omega, or W if you want to call it that.
And that's the amount of time it takes to go from one peak to another peak?
Yeah,
Okay.
that's our period. Right, good clarifications. Cool. So for a circuit like this, if we kept the voltage the same, if we kept the inductance the same, but we changed the frequency that this source was operating at. So instead of 120 hertz, we're working at 1,000 hertz. How is that going to change how much current the circuit gets? So inductors resist change in current. So trying to make the changes happen very rapidly is harder. To get there with a little bit of algebra, we divide both sides by our angular frequency and by our inductance. As the frequency or angular frequency increases, current decreases for constant voltage and inductance. And we can use this. We've got a relationship between voltage and current. So it kind of looks like Ohm's law in that way. It's not, but a relationship between voltage and current, kind of like Ohm's law. So a different way of transforming it is looking at this quantity right here. Voltage is equal to current times resistance as a resistance-like quantity. So in Ohm's law, V equals IR. Where the angular frequency times the inductance is holding the place of what resistance would be if this was a resistor instead of an inductor. So we actually can give that quantity a unit of ohms. So the angular frequency times the inductance is called the inductive reactance. Where reactance is getting that capital X. It has units of ohms. It's not a resistance, but in a lot of ways it functions like one.
So just so I know, it was that it would decrease.
Yes, it would
Okay,
decrease.
that's- thank you.
So this is the formula for inductive reactance. So we can put it in our amplitude or our RMS equation. But we can't do this. Any ideas why the bottom equation doesn't work? That the amplitudes are related to each other by this inductive reactance, their RMS values are related by their inductive reactance, but at any given time, you can't say that they relate to each other with their inductive reactance. These are all good and happy. This one's bad and wrong.
I think because V and I are DC voltage and current, right?
You are very, very close. They are the, yes, I'll take that. They are the instantaneous voltage and current. So it's whatever the voltage is at any given time is V with no subscripts, and what I with no subscripts, whatever the current is at a particular time. So they are time varying, and they time vary differently. Remember, you can have zero current when you have a non-zero voltage, and zero voltage when you have a non-zero current. So their amplitudes relate to each other. The RMS values relate to each other, but at any given time, one of them could be zero and one of them could be non-zero. So it doesn't work. And what about a capacitor? So for a capacitor, the voltage across it is equal to the charge on its plates divided by its capacitance. So if we have an AC voltage source, hooked up to a capacitor. This time we can have our current be defined as the positive rate of change of charge. And just let our current have its current amplitude to cosine of omega t. So then the charge is going to come from the integral of current. So integrating cosine is going to give us sine. So this time, if we make our third of these graphs time and current, taking that same cosine curve, our voltage is going to be following the current. So after current has built up for a while, then you get substantial voltage. It's not when you get the most current, it's when you get the most current that has flowed. So this time, our current leads the voltage. Our red cosine curve is doing what that black sine curve does a quarter phase earlier. It hits a peak, then the voltage hits a peak. It hits its minimum value, then the voltage hits its minimum value. So across a capacitor, the current leads the voltage by 90 degrees or by a quarter phase. So for a capacitor, let's see if you can guess, predict, work through how the current that you would get in that simple circuit would change as frequency was increased. Most you got it this time around. At a greater frequency, you actually get more current if you have a capacitor. So let's look at the reverse to make it more clear. If you're working at a very, very low frequency, you're going to fill up the capacitor. And if your voltage is changing slowly, that means the amount of charge that you'll be able to store in it with a slowly increasing voltage will increase, but it will increase slowly. So you'll reach the same amount of charge across the capacitor, but if you have a long time to do it, you'll do it with a small current. And if you're going to hit the same amount of charge across the capacitor in a short period of time, you need large currents to get the same amount of charge built up. So yeah. For a capacitor, for a given voltage, there's going to be more current at high frequencies than low. So if we're just moving to amplitudes, where 1 over our angular frequency times our capacitance, again, is our resistance-like term, where V equals IR, V equals voltage amplitude equals current amplitude times 1 over omega C. So this does have units of ohms. And we call this quantity a reactance again, but it is known as the capacitive reactance. So for an inductor, its resistance-like quantity was the inductive reactance. For a capacitor, it is the capacitive reactance. If you want it in terms of frequency instead, so we could rewrite our original equation. And again, it would be perfectly fine to use RMS values instead of peak values. But just using the instantaneous values does not work because they reach their peaks at different times.
What are the units of the large X?
Ohms.
Thanks.
So yeah, 1 over a farad times 1 over a second works out to be ohms. Oh, sorry, 1 over a farad times 1 over a second. So a farad second would be in ohms. So let's see if you can compute. So remember, this is not the 60 hertz is not an angular frequency, it's a frequency. So you get it right, you need to convert to angular frequency or use 2 pi times it. All right. So our inductive reactance. Angular frequency times inductance. 2 pi times our frequency times our inductance. And the capacitive reactance. Around 2.65 ohms. Good on this. L for inductors, C for capacitors. So yes, sometimes I guess L's and C's, I should draw them more distinctly. L always for inductors, C always for capacitors. So uses of this. One way you can use capacitors and inductors is not every voltage signal you get is a perfect sine wave. You could have something like this as your voltage over time. Could happen. Or you could have something kind of like this. Or this has a clear low frequency component, the slow variation, and a clear high frequency component, the up and down quick changes that happen on top of that. So if you have a signal like this, you can use a capacitor or an inductor to filter out what you want. If you use if you have a source like that and you put it through a capacitor, it works as a high pass filter. You get the current from these small variations passing through this pretty easily. But because it has a high reactance, for low frequency signals, very little current due to the slow variation will pass through. High pass. You could use an inductor. And if a signal like this were fed through an inductor, it would resist those rapid changes in voltage. So it's very hard to make very rapid changes in the current. So those very high frequency changes would lead to very little current getting through, but the slow overall change would get through pretty easily because it has a low reactance for low frequency signals. So this would be a low pass filter. So splitting up signals and analyzing them, a lot of people would do it, figure a lot of out from any sort of a signal can get turned into a voltage over time. A common application of this is for speakers. If you have a tweeter and a woofer, and this is your voltage over time, which you would want to turn into, at some point, a sound wave. You could use filters like this to feed the higher frequency component to the speaker that's good at making high frequency noise, and the low frequency component to the speaker that's good at making low frequency noises. It's kind of a cool thing. All right. Let's
So
go ahead.
the low pass filter would be better for the second graph. Is that right?
So it's all about what you want to see. So after you pass through the filters, the top one, you might get something that looks like that. And the bottom one, you might get something that looks like that. We haven't completely killed out the fast changes or the slow changes, but you mostly see the rapid variation if you put it through a capacitor, and you mostly see the gradual variation through the inductor. Neither of these is good or bad. It's just, what do you want to make it through? So there are times when you'd want to have high pass, and there are times you want to have low pass. I tried to make a part of a detector once. Didn't work very well, but there was a signal from, there was a flash of light, and there was something that could detect those flashes of light. And after it made it through the circuit, due to noise in the circuit, instead of getting a voltage over time, signature like this, there was just very small amounts and some noise was making so that I was getting, something that looked kind of like that. And I wanted to figure out when this pulse on the whole was coming in. So those jagged peaks were interfering with my ability to do that. So if I could use a low pass filter and turn it into something that looked more like this, It'd be much easier to time when that was happening. Just passing it through an inductor helps smooth it out.
Okay, one more thing. So, would that be like the voltage across the inductor? Because like you can't change the voltage because of the loop law, right?
So let's say that after you go through this, there's, maybe a resistor there. So just a low resistance resistor there. And then, yeah, maybe you'll complete the loop after that. So you could look at your voltage across this resistor.
Okay, so you're not, so the voltage across the entire circuit stays the same, but then you're smoothing it out like after the,
Yeah, so yeah, we could look at the voltage across this resistor.
okay, got it. Thanks.
Yeah. So what makes it on through it? Let's put them all together. Got an AC source. Got a resistor. Got an inductor. And we have a capacitor. All of our Christmases at once. Wonderful, wonderful things. All right, so loop ruling this. The voltage from our source needs to be equal to our voltage drop across our resistor plus our voltage drop across our inductor plus our voltage drop across our capacitor. But as we saw, the voltage from the across the resistor is exactly in phase with the current flowing through this circuit. The voltage across the inductor lags behind the voltage, and the voltage across the capacitor leads, I'm sorry, the current, the current is going to lead the voltage across the capacitor, and the current is going to lag the voltage across the inductor. So we can't use that the voltage amplitudes sum up to the voltage amplitude across our source, because they have peaks at different times. So if they all peaked at the same time, then yeah, they would peak, the sums would work out, but they don't. So the sums of the peaks will be more than the peak of our source. So if we just have two of them, so let's have our voltage VR. So start with our current. That's the same through all of them, so that's just kind of be the anchor point. So for our current, it's going like that. And the voltage across the resistor is going to be in phase with it. The voltage across the capacitor is going to lead it. Sorry, the current is going to lead the voltage. So our current is going to lead the voltage. And for the inductor, the voltage is going to lead the current. So the current lags the voltage. So using a voltmeter across each of those three elements, you could find this voltage over time relationship. And all of these are happening. So the voltage across the source needs to be the sum of the voltage across the three elements there. So if we just add those three graphs together, we're going to end up with something zero. This. Kind of like that. Probably should be a little bigger in magnitude than that. Yes, it should. There we go. Kind of like that. There we go. This is not an easy thing to do. Figuring out how all of these things at different phases would add together. Mathematically, these rules are working out. Not conveniently, but the voltage across the individual elements will be the voltage of the source. Because they all are getting the same current in this RLC series circuit, having current be the thing we work off of is good. There's a tool that makes working with these circuits a lot easier than trying to graph it like this. Just trying to graph it in time. And this tool is the phasor diagram. if we have just a XY coordinate system, and we want to describe a cosine function or a sine function. If we make a triangle, and we have a vector of constant magnitude, we can think of the sine and the cosine as being related to the y and x components of this. So current times the cosine of omega t, we can keep our current magnitude as a constant because it is, and then make an actual triangle to figure out the cosine component we need. So we're going to make a geometric picture of what omega t are, where this is omega t, this is I naught as the hypotenuse, and adjacent over hypotenuse is going to be the cosine. So our current over our current amplitude is cosine omega t. And this doesn't seem to offer much at the moment. But what's going to happen if we look at this graph and allow time to increase? Well, then omega t increases, and this vector, our current amplitude, is going to have a constant amplitude, but it's going to rotate. So we've got a vector which is rotating in this space, and we only care about its x component. So when it is pointing straight up, we have the same current amplitude because that's a constant, but at that moment, our current would be 0. When omega t makes it to a value of pi, the cosine of that is -1. So our current is going to be minus our current amplitude. And then goes to 0, back to our original value. If you don't want to think of this as xy, you can think of this as real and imaginary. If you hate that, don't want that at all, you can think of it in terms of x and y, whatever is easier for you to look at. What we just care about is the x or real component. That's what our current is at any given time, because we've got a cosine there. Is this okay? At the moment, it probably seems I hope it seems like it kind of makes sense, but doesn't seem useful yet.
That's what it seems like.
Okay. All right. That's as much as I could hope for at this point. Our voltage across the resistor is always going to be in phase with the current. It has the same cosine function. So whenever our current is maximized, our voltage across the resistor is maximized. So we can get VR, voltage across the resistor, from that cosine. That's a-okay, not all that interesting or useful. Where it becomes useful is, let's look at our inductor. So that inductor is not in phase with the current. The inductor is leading the current. So it's 90 degrees ahead of the current, or a quarter phase ahead of the current. We've got that orange peak here, and we can see the red current happens after. The red peak happens after it. So if we wanted to plot our voltage across the inductor in this, oops, that was bad and wrong. We would just put it 90 degrees ahead. And if I wanted to put in the voltage across the capacitor, the voltage across the capacitor is always 90 degrees behind the current. The current peaks, then the voltage across the capacitor peaks. So that would be our voltage across the capacitor. Oops. Where if we imagine our current rotating around, by the time the current has gotten to its pointing up along that y-axis, that's when we're going to get that maximum for voltage across the capacitor. So we can see that when our current has reached 0 in this picture, current reaches 0 there, that's when we get the maximum across the capacitor. At that same point, when our current first reached 0, if we look to our inductor, that's when we get our biggest negative. So if we rotate all of these vectors together, then we get our negative peak for voltage across the inductor. So using this phasor diagram for just one quantity at a time is pretty silly, but using them all together is super useful. So it was kind of a pain to try and add these three sine or cosine functions together to get the voltage across all of them. But doing them in the phasor diagram, it's not bad at all. It's just addition of vectors. So if we add the blue vector and the yellow vector together, we'd get a vector like this. They're in opposite directions, but the yellow one's bigger. And if we added that to the green vector, we get this. So voltage across the source, in this case, is going to be leading the current, not by as much as the inductance does, but still a little. Our magnitude we can get by using the Pythagorean theorem on this. If we know the difference between the magnitudes of these two vectors, and we know what our voltage across the resistor is, because they're at right angles, a squared plus b squared equals c squared, that'll give us the voltage of our source. So this tool lets us figure out how the voltage from our source is going to relate to its current. And it gives us a way of finding how the voltage of the source in magnitude relates to the current magnitude. Pretty cool.
It actually is pretty cool.
It
'Cause
actually is pretty cool. You are
Yeah.
right.
it's almost like we're just going back to what we started with physics, like the very first thing we learned, just adding the vectors up and then getting one
Yeah.
that's as a resultant.
So phasers, not explicitly a phaser lab, but the lab of, so if you're the earliest lab group, your next lab, and if you're not the earliest lab group, the lab after your next lab will deal with how these circuit elements work together in with an AC source feeding them. So we'll use a function generator to make a sine wave and look at voltages across circuit elements. So yes, we will get a lab to look at this, but phasers are kind of abstract. So one of the most abstract things to deal with, and we deal with fields all the time. So it's a really cool tool, but yeah, if it doesn't click immediately, that makes sense. It's kind of a mathy way of looking at it, but it's a cool and powerful tool. So if you wanted what the voltage across the source was at any given time, you would just, oops, go back. Get the X component or the real component. So that would be our voltage across the source. So to put some numbers to this cool picture, our voltage magnitude from the source, well, we got it by adding these vectors together. So if it was looking at a different point in time of this graph, the t equals 0 point. So t equals 0, we're going to have voltage across the resistor voltage across the capacitor going down, and voltage across the inductor going up. And if this point here is what we get from adding together our positive Y inductor and our negative Y capacitor at that same height. We have our voltage across the source. So Pythagorean theorem, that's going to be the square root of our voltage across the resistor squared. Our voltage amplitude across the resistor squared. plus the square of the difference of these magnitudes. Oops, difference. The difference squared. So this bit here is this side of the triangle. And this bit here is the height of the triangle. All right, voltage across the source. We can do even more with this. All of these are current dependent quantities. So our voltage amplitude was current amplitude times resistance. And our voltage amplitude across the inductor is current amplitude times inductive reactance. And our voltage amplitude across the capacitor was current times capacitive reactance. So I'm just going to pull current squared out of all of those terms. And when it leaves the square root, its square goes away. So we now have a voltage current relationship for the resistor, capacitor, and inductor all working in the same circuit in series, which is an accomplishment. If you only have two of them, you can still use this. It's just one of those terms will be 0. I guess you could use it if you only have one, but it seems like unnecessary work. So this quantity here is filling a resistance-like term. If we've got V equals current times something for the whole circuit. And we're going to call that the impedance of this circuit. So how much does this circuit resist current from an AC source? So capital Z is impedance, and that is equal to square root of R squared plus the inductive reactance minus the capacitive reactance squared. If you want to break it down more into where those reactances came from. Oh, wow. My C's and L's are unacceptably similar. There we go. Now C and L are different. Break it down a little bit farther. Impedance is equal to the square root of R squared plus our inductive reactance minus our capacitive reactance squared. So this would also be measurable in ohms. It is frequency dependent. because both the inductive reactance and the capacitive reactance depend on frequency. But you can just plug it into here. So this V equals I naught would just be V equals I naught Z. So once you do all the work to find this impedance, you've got a current voltage relationship. However, they're not necessarily in phase with each other, so you can't use it for instantaneous values. All right, let's compute one of these. So a lot going on. First things first, find your angular frequency. And then use that to find the impedance. So this is just going to be an LRC series circuit. Go for it. Right, so for the angular frequency, (2000) pi inverse seconds. So our impedance is going to be equal to square root r squared plus the square of the difference of our reactances. Or that. And where our resistance is 150 ohms, the inductive reactance will be our angular frequency times 60 millihenries. Or 0.06 henries. And this is approximately 377 ohms. And our capacitive reactance is our angular frequency, the inverse of our angular frequency times our capacitance, and that was approximately 199 ohms. And this works out to be around 233 ohms. Good on this. So it's possible that the total impedance is actually less than the inductive reactance, because the capacitive reactance actually works to counter it. It can never be lower than the resistance, though. That presents a floor. All right, let's go back. Yeah, those prefixes, they're not hard. They're just easy to get wrong.
And they are not insignificant.
They matter a lot, yeah. Difference between an N and an M, just one little hump, but it's a power of a million. So power, we need to be careful with getting power on this. We can't just use v squared z or v squared over z or I squared z. So the reason for that is how the phases work out. So power that's solid. At any given instant, the power being used by something is the current going through it times the voltage drop. Because the voltage drop is how much energy each charge gives off as it goes through, and the current is how many charges go by per second. That gives you how much energy used per second. So that is A-OK. But if we want our average power, we can't just multiply our average current times our average voltage. For an extreme case of that, if you have just an inductor or just a capacitor, the average power is actually 0 because the current is completely out of phase with the voltage. So it gets energy put into it as you increase the current through an inductor or charge a capacitor, and gives that energy back as the current through the inductor decreases or the charge leaves the plates of the capacitor. So the phase between them matters. And we can figure out what that phase is. So the tangent of this phase is going to be what we get from the difference of our voltage across the inductor minus the voltage across the capacitor, divided by the voltage across the resistor. And just like we did for getting to Z, all of these terms can be divided by the current. So our current, just fine. We can express our voltage in terms of our current now. It might be easier to get this expressed instead of as a tangent, as a cosine. So for the cosine of this, it would be the voltage across the resistor as the close side, and Z makes the long side. So cosine of V. Is resistance over total impedance. So it's only the resistor that's going to be dissipating energy. So this is going to give our voltage across the resistor in relation to the voltage across the whole system for voltage amplitudes. So if our average power is going to be IRMS squared times our resistance, this still holds because this is the average power dissipated by the resistor. And if the resistor is the only thing that's dissipating power, I squared R still works if we use IRMS. And this ends up being equal to R is going to be equal to Z times the cosine of phi. Using this equation, multiplying both sides by our impedance Z. Cosine of our phase angle. However, IRMS Z is equal to our voltage. The whole point of this was it gives us our voltage current relationship. So we're going to take one of those currents, turn it into a voltage. So it's not just IV or even IRMS, VRMS anymore. How far the voltage is out of phase with the current also comes into play for the power usage. So if this cosine term is 1 and the voltage is exactly in phase with the current, that'd be what you'd get if you had just a resistor or an inductor and a capacitor that exactly cancel each other out. It would just be RMS voltage times RMS current. But as the resistor becomes less and less a significant factor of the total impedance, the phase between them matters more and more. So this is sometimes known as the power factor, because you could have two circuits that have the same RMS voltage and RMS current that dissipate different amounts of power. Because if it's dominated by an inductor, most of the energy that gets put in gets received again. Or if it's mostly due to resistance, it's just dissipated.
So one more time, you're finding phi by getting the direction of V naught and subtracting WT from that.
No. So omega t is irrelevant in this moment. So we're getting the angle not between where our current vector is pointing is arbitrary. It changes over time. So yeah, we're getting the angle from V naught to current.
So how do you find that? Like what is phi?
Phi
Like,
is
are
the
you
angle
just given-
between V naught and current.
Would you be given phi or?
No. So ways you can calculate it are there, or these are ways of getting to it. That's how you can find it.
Okay, got it.
So from the bottom one, you can see the bigger the resistance is as a fraction of your total impedance, the closer that cos phi term is going to be to 1. So a different way of expressing it, if you don't want to think about phi at all, we can just change that to R over Z. And that'll work just fine. All right, that is a lot for today. So this will be our stopping point. We will work more with AC circuits next week. If you want it, work through just one of the examples or a problem from the book just to help this stick, because it's a cool tool, but it's kind of out there. Any last questions before we are done for the day?